Hello everyone. Today we're going to talk about a very sort of common problem that comes up in interviews and algorithms classes, and it's just longest palindromic substring. Okay, and it's a pretty straightforward problem where, given the definition of a palindrome, which is a string that is the same in the forward direction as it is in the reverse direction, or any number or what have you. Find the maximum length palindrome substring within that string. And a substring, could be the entire string. That's a substring of itself. So let's just get started right away. What's the sort of key idea here? So the key idea is sort of the main idea behind a lot of dynamic programming problems, and the sort of dynamic programming paradigm is using what we've already computed to immediately compute the next step. So how does this help us? Well, if you have some string and you know that the sort of center in between two characters is a palindrome and the two characters match here, then you know it's a palindrome, right? And you could write this out and prove it to yourself by hand. Alternatively, if the center is not a palindrome, even if the two characters on the outside match, it's not a palindrome. And the third case, right, is the two characters on the ends don't match, in which case the center doesn't matter at all. It's not a palindrome no matter what. So what are we going to do to solve this? The first thing we want to think about is, how do we store our sort of results? I mentioned that we're going to use what we've already computed to sort of conclude or compute other things in the future. So in any dynamic programming problem that you find, you're going to be storing data in a matrix, a list, a dictionary if you're using Python, hash table, whatever. All of that is going to be storing the result in somewhere. The next sort of question you have to think about is, okay, how many things do I need to store? And what do I need to store? So in our case, we want to know this sort of cloud area. And this is really some index I is some index j, a substring, right? This is a substring of our string. So we're going to compute for every substring ij, we are going to compute, is I to j a palindrome? And you'll see why that helps us. Is 0 to 0 a palindrome? Yes. Is 1 to 1 a palindrome? Yes. 2 to 2 a palindrome? Yes. Any character of itself is just a palindrome, right? Any string of length 1 is a palindrome by definition. So what else do we have to fill in this table? Well, we don't actually need to know any of this. Why don't we need to know any of this? Well, because we're not that interested in indices that are going backwards. We don't care about 1 to 0, right? If our index is I to j, if we're here, 3 to anywhere here in this row is going to be below it. 3 to 2, 3 to 1. We don't care about that. So we actually only need to fill out the top half. Now, how are we going to fill this out? The order in which you compute things with dynamic programming problem is just as important as what you're actually computing a lot of the times. So what do we need to know? Well, we need to know the indices I, j, they're in between whatever we're evaluating. For example, if we tried to evaluate 0 to 6, a to b, we wouldn't be able to do that. Why not? Because we haven't evaluated 1 to 5 yet. So we're going to fill out this sort of half matrix, this diagonal upper triangle, in a way that makes sense, and then we can sort of see the logic after that. So is 0 to 1 a palindrome? Can we answer that question? Well, automatically a does not equal b. It's just false. We don't care about anything else. We don't even need to encode logic. It can't possibly be a palindrome. We don't need to code complex logic. Let me put it that way. Is 0 to 2 a palindrome? Well, it is a palindrome. How do we know that? Sorry, it's not a palindrome. 0 to 3 is a palindrome. So A does not equal B. False right away. I was jumping ahead. Is 0 to 3 palindrome? Yes. A, B, B, A. A does equal A, but that's not the only condition we need. We also need to know, is 1 to 2 a palindrome? How do we know from this table if 1 to 2 is a palindrome? Well, that value is going to be here, okay? Index 1 to index 2. But we haven't filled that out yet. So we need to fill this out. So is 1 to 2 a palindrome? Well, this is sort of like a small edge case, and the answer is yes. And the reason why it's yes, right, is because B does equal B. Okay, that's a necessary condition. But it's of size 2, right? It's even. It doesn't. We can't look at. There's no in between index here, right? So in reality, the index that's relevant to this, I don't know why it keeps doing that. The index that's relevant to this is actually just this character itself. So whenever you're sort of against this diagonal and you're considering palindromes of size 2, you're just going to look at the character next to it. Are these characters the same? Yes. Okay, true. And that makes sense, right? 1 to 2, B is a palindrome. Now what do we fill out? Well, can we answer the question 0 to 3? Turns out we can, because we've evaluated 1 to 2. 1 to 2 is right here. A and A also equals each other. So this is true and true. So we first ask, are these characters equal? True. And then we look up the cell. And here's the pattern that you may see. We look at the cell to the bottom left, right here. So we can just keep filling this out, doing this simple and conjunction of logic the whole way. Does B equal A? Nope. False. Does B equal A? Nope. False. Done with that column. Right? 2 to 3, B to A, not a palindrome. 0 to 4, does A equal F? Nope. Does B equal F? Nope. B equal F? No. A equal F? No. That makes sense, right? You can't possibly make a palindrome if we end at position 4 from anything. Can we make a palindrome if we end at position 5? Well, if we start from 0 to 5, that's false, right? They do equal each other, but this in between 1 to 4 is not a palindrome. Okay, how about 1 to 5? B, well, B does not equal A, that's false immediately. How about 2 to 5? Also false. How about 3 to 5? AFA, well, that is a palindrome. A does equal A, and the bottom left cell is also a true. So this is true. What about 4 to 5? F to A? No, false. They don't equal each other. And you can see I've sort of highlighted our winning sort of palindrome here that we have yet to discover, right? So let's see if we discover that. 0 to 6, is that a palindrome? No. 1 to 6, is that a palindrome? Well, they are equal, but we haven't, the center is not a palindrome, so that's false. 2 to 6, is that a palindrome? Well, they're equal, and 2 to 6 is also a palindrome, so that's true. And then A does not equal B, and F does not equal B, and A again does not equal B. So we're done. Now, how do we remember our answer? How do we compute our answer, right? The problem asks us to return the actual string. So you could, go back and look at all the trues and see which one's the biggest, and sure, that would actually end in the same sort of runtime. But the more simple way of doing it is just every time you compute a true, you just remember, hey, I was 0, I equals 0, j equals, that's a very bad j equals 3. So we have a palindrome of size 4, 3 minus 0 plus 1. And we could remember these indices and then return that substring at the end. And as we're going along and we discover this one, hey, this is 2 to 6, BAFAB. Well, so is, J is 6 and I is 2. 6 minus 2 plus 1, that's size 5, right? So hey, this is greater than 4. So let's just replace all of these numbers with these. And we could just, return S of 2 to 6 at the end, or 6 plus 1 in this case, because we want to include the end. It depends on your language, right? But you just return the substring that is relevant. So that's sort of one solution, and I encourage you to skip to the end if you want to see the code for the other solution, as well as I'll sort of do a walkthrough of the next solution. And the next solution I think is a little bit more intuitive. If you're not really interested and you just want to code this up, go ahead. I think this is like pretty simple logic, but for the remainder of the video, I'm going to be talking about sort of a different idea. And this idea, I think, is a little bit more intuitive, and it shows that you can actually think about problems in multiple different ways and still have the same runtime. So this way is actually not going to be any dynamic programming at all. And I'm a little bit surprised that I don't see people think of solutions that sort of revolve around this concept. So what if we just ask the question, for every index in the string, let me go look up the string again because I forgot, because my short-term memory is awful. A, B, B, A, F, A, B. What if we just asked the question, what's the longest palindrome that I could achieve at any given index? So let's do that. A. Well, that's 1. Right? If we think about this algorithm of what it means to be a palindrome, if we fan out by 1 each time on both sides, maybe we'll discover a palindrome from that index. So, and there's going to be a flaw in this algorithm, so don't sort of think I'm leading you down the wrong hole. This is just sort of going to be an example. So let's do it for B. Let's fan out by 1 on each side, A and B. They're not equal, so this is only size 1. Clearly false, right? Because you can construct a palindrome from that character, but let's just keep going. How about this B? Fan out 1 on each side. Don't equal, that's 1. How about this A? Does B equal F? No. How about this F? Does A equal A? Yes. So we can fan out again. Does B equal B? Yes. And then we get to the end of the string. So we discovered a size 5 substring here. What about this A? Can we fan out 1 on each side, F and B? Yes. Not a palindrome though. 1. So size 1. And this B is on the end. Must be 1 as well. So we actually do discover the correct palindrome, but we're not actually computing the correct we're not computing all of the palindromes, right? Because what if this just wasn't here? Then we would have failed, right, to discover the correct palindrome. So what's the sort of key idea here? Well, one is, this is fine for odd palindromes, right? Because odd palindromes will have some center number or center string, and then some stuff on the sides. But even palindromes like B, B, A doesn't have a center. The center is actually these 2 characters, both of them. So what you can do is, and I won't sort of go through the whole thing, but you can evaluate this in terms of, okay, find me the longest odd palindrome and find me the longest even palindrome. Right? So if you want to know the longest even palindrome, you just go through the list and you look for indices that are next to each other that have the same value. So when you get here, you look up ahead and you say, hey, does B equal B? Yes. Okay, so this right here is a palindrome, right? We have a palindrome size 2, and then you just do the same algorithm that I sort of described, where you fan out by 1 on each side. And you would discover these A match, and then you'd have a palindrome of size 4. Right? So that sort of logic is actually what I've written in the code, and sort of I'll show this now, and you can read it and or stop and screenshot. Also, all of the code will be on GitHub. If you want to know sort of exact implementation details, I'm honestly not the cleanest coder. I sort of, when I code algorithms, I just kind of throw it together. This code isn't necessarily super fast, it's not super optimized, but it does land right in the middle of the pack with no optimizations whatsoever. It doesn't use any extra memory. Okay, that's the important part. I'm not making a matrix with this algorithm. It's just remembering the longest palindrome it finds. And that's it. So if you liked this video, like, subscribe, what have you. Thank you for watching. I'm going to try to do a lot more frequent videos and sort of get content on a regular basis. So again, thank you, and hopefully see you in the next video.